So I actually had a minor surgery yesterday morning, so I'm not sure if I can get through the entire class today. I'll still try to do so, but if I feel uncomfortable along the way, then we'll maybe have to end early and pick up again tomorrow. Okay. All right. So last time we're talking about the existence of the Fourier series representation for periodic continuous time signals. Okay. So namely, we want to know when or what types of periodic continuous time signal x of t can be represented as this summation of ak e to the j k omega naught t. Okay. Now, when you're asking whether or not such an expression exists, right, you can see that this expression involves a summation over infinite number of terms. So when you're asking whether or not this expression exists, you're essentially asking whether or not the convergence of this summation, right, as the number of terms that you add up go to infinity, will eventually converge to this function x of t. Okay. Now, you could be looking at convergence for all possible values of t, right? So you could be looking at this everywhere convergence where the right-hand side converges to the left-hand side for all possible values of t. Okay, but this convergence is very challenging to achieve. Okay, and probably is not necessary in many engineering applications. Okay, so instead of looking at convergence everywhere, we looked at two other alternative notions of convergence. Okay. All right. So one notion of convergence is convergence in the sense that the energy in the error vanishes as this capital N goes to infinity. Okay. So if you're looking at this notion of convergence, then it can be shown that any periodic signal with finite energy over a single period satisfies this convergence, right? Meaning that any periodic signal with finite energy over a single period has a Fourier series representation under this notion of convergence, right? The convergence in the sense that the energy in the error vanishes as capital N goes to infinity. Okay. Now, alternatively, Dirichlet gave us another notion of convergence, saying that actually this Fourier series representation converges to x of t, except at isolated points at which it is discontinuous, right? If the signal satisfies the following three conditions. So condition one is that the signal should be absolutely integrable over one period. Secondly, this signal should have bounded variation, okay? Bounded variation over a finite interval. Some signal like this, where the frequency increases to infinity as it approaches zero, would have infinite maximum minima over a period, and therefore does not satisfy Dirichlet conditions. Okay. Now the third condition is that there should be only a finite number of discontinuities, right? So if a signal satisfies these three conditions, then Dirichlet showed that this Fourier series representation converges to x of t almost everywhere except at isolated points at which there is discontinuity. Okay. Now these discussions tell us that almost all signals of interest in practice does have a Fourier series representation, right? So this sort of justifies the usefulness of this type of representation. Okay. Right. Now, last time we also went through a little history of the development of this Fourier series representation. Now, the source of argument, as we discussed, is mainly in the convergence of signals with discontinuities, right? So if you recall, Lagrange argument that the Lagrange argument for rejecting this theory is that he believes the pluck of a string, right, will cause discontinuities in the signal that you cannot represent using these sinusoids. Okay. So sort of to address this concern, Michelson tried to look at the convergence of this truncated Fourier series for different values of n, okay, for a particular periodic square wave, right? So starting from n equal to 1, right, we can see that when n is equal to 1, there is only one sinusoidal component, and this x sub n of t naturally deviates from this square wave quite large. Okay, but as n increases, right, this approximation given by the truncated Fourier series becomes closer and closer to the shape of an actual square wave. Okay, but if you look at these signals that we get, you will see that there will be ripples. There will be ripples along this along this horizontal line, and that there is a overshoot on the edges, which maintains to be about 9%, okay, regardless of what the value of capital N is. Right. So you can see that as capital N increases, these ripples becomes smaller and smaller, and eventually will converge to the flat surface of the square. But this edge, right, this overshoot at the edge actually does not decrease as capital N increases. Okay, and this overshoot by 9%, this observation is called the Gibbs phenomenon. Okay, now even though this overshoot always exists, even as n goes to infinity, right, you can see that this overshoot is pushed closer and closer to the discontinuity point as n goes to infinity, right? So as n becomes, as n goes to infinity, right, even though the overshoot still exists, right, it will eventually exist only at the discontinuity point, right, which still satisfies the convergence, the notion of convergence described by Dirichlet. Right, so Dirichlet says that this converges at almost all points except at points of discontinuity. Okay. Okay, so this is where we ended last time. Okay. Now, So through these discussions, we now know that almost all periodic signals that we may encounter in practice has a Fourier series representation. Okay. Now we can derive various common properties of Fourier series representation. Okay, that can be useful for us to analyze or compute the Fourier series of more complicated signals. Okay. Now, first of all, let us start by giving a notation for a periodic signal and its corresponding Fourier series. Okay. So suppose that AK is the Fourier series coefficient is the set of Fourier series coefficients for the signal x of t. Then we denote this by x of t, AK with a double-headed arrow, and Fs on top to denote Fourier series. Okay, so when you see this notation, right, this is saying that AK is the Fourier series coefficient of x of t. Right, so given x of t, you can extract out AK by using the formula that we derived previously, and given AK, you can reconstruct x of t through the Fourier series representation. Right, so this is a so-called Fourier series pair, right? A pair of signals and its corresponding Fourier series coefficient. Okay. Now we can show several common properties of these Fourier series representation. Now, first of all, starting out with linearity. Okay. So suppose that we have two signals x of t, y of t that are both periodic with period capital T. Okay. So it is critical to have both of these signals have the same period capital T. Okay, so that they can be represented by the same set of harmonically related complex exponentials. Okay. So using the same set of harmonically related complex exponentials, x of t, we assume that x of t has Fourier series AK, and y of t has Fourier series coefficient BK. Okay. Then you can show that the Fourier series, so you can show that for z of t, that is equal to a linear combination of x of t and y of t with coefficients a and b, the Fourier series coefficient of z of t will be equal to a linear combination of the Fourier series coefficients of x of t and y of t respectively with the same linear combining coefficients, capital A and capital B. Okay. Now notice that first of all, in order to have a Fourier series representation, you must first show that z of t is also periodic with period capital T. Okay. Now this is quite straightforward to show. Right. So note that if you take z of t plus capital T, right, which is ax of t plus capital T plus b of yt plus capital T, right? By the periodicity of x and y, you can write this as ax of t plus b y of t, and by definition, this is z of t. Okay, so hence, z of t is periodic with period t. Okay. So if z of t is periodic with the same period, capital T, then you can express it in terms of the linear combination of the same set of harmonically related complex exponentials. Okay, so in this case, we can obtain the Fourier series representation of z of t as summation ck e to the j k omega naught t k from minus infinity to infinity for omega naught, that is 2 pi over t. Okay. And then this ck here, okay, which is the Fourier series coefficient of the signal z of t, which you can obtain by taking 1 over t integral z of t times e to the minus j k omega naught t dt. Okay. Now you can substitute z of t with this linear combination of x and y above, and this becomes a 1 over t x of t e to the minus j k omega naught t plus b 1 over t y of t e to the minus j k omega naught t dt. Okay, and you can see that this integral here gives you the Fourier series coefficient of x, which is ak, and this second integral here gives you the Fourier series coefficient of y, which is bk. So therefore, this gives you ak plus bk, which is what we wanted to show here. Okay. So I wanted to, point out, one thing that people often neglect. So one important thing is that here x of t and y of t must both be periodic with the same period, capital T. Okay. So, the reason that this is necessary is because if you want to sort of perform computation on the Fourier series coefficient of these corresponding signals, then these coefficients should correspond to the same set of harmonically related complex exponentials. So if the two signals have different periods, then you would be using different set of if they have different periods, then their original Fourier series coefficient may be corresponding to different set of harmonically related complex exponentials. Okay, so in that case, you may have to find the common period of x and y in order to find the corresponding Fourier series coefficients for that common period. Okay. So this is actually, often assumed unless mentioned otherwise, right? So this is often not mentioned explicitly, but you should always be aware that this is a underlying condition that must be satisfied. Okay. Now, another common property that we often encounter is time shifting. Okay. So suppose that x of t has Fourier series coefficient ak, then a time-shifted version of x of t, shifted by t naught, has Fourier series coefficient bk that is equal to ak times e to the minus jk omega naught t naught. Okay, or if you substitute omega naught with 2 pi over capital T, then this is what you get. Right. So to show this, first of all, right, in order for x of t minus t naught to have a Fourier series representation, this must also be periodic, okay, with period t. Okay, and this is also easy to show, right? So in fact, you can show that, if you have x of t plus capital T minus t naught, right, by the periodicity of x of t, this is equal to x of t minus t naught. Okay, so hence, a time-shifted version of x of t is also periodic. Okay, and then to find the Fourier series coefficient by bk, we take 1 over t integral x of t minus t naught e to the minus j k omega naught t dt. Okay. Now we can perform a change of variable where we set tau equal to t minus t naught. Okay. So in this case, this becomes integral of x of tau e to the minus j k omega naught, where t becomes tau plus t naught. D tau. Okay. Right. So this t naught has nothing to do with tau, so I can bring this term outside of the integral, which gives me e to the minus j k omega naught t naught times 1 over t x of tau e to the minus j k omega naught tau d tau. And this integral here gives you the Fourier series coefficient for x of t. So this becomes ak e to the minus j k omega naught t naught. Okay, so you can see here that a time shift in the signal x of t gives you a Fourier series coefficient that has the same magnitude as x of t, but now with a phase shift of k omega naught t naught. Okay. So this shows that a time shift in x of t corresponds to phase shift in the Fourier series coefficient. Okay. Okay, so Do we have any questions up to this point?那个张允成在吗？还是我名字念错了？
你说张云成吗？
张云成，对。
哦，好，在。
对，就到这边有没有什么问题？
目前没有问题，对。
OK， 所以你可以了解说这个，就是说这样的一个 relationship 是怎么样求得的吗？就是说为什么 BK 会是 AK 乘上一个这个exponential 的这个phase shift？
可以，就是下面有推导出来嘛，就经过一个超等于 t 减 t 0转换，然后就会求出来。
OK， 好，谢谢。所以我想这两个 example 其实大部分这些 example 都是蛮直接可以这个推导的就是从这个 Fourier series 就是我们前面给的这个怎么样 extract 这个 Fourier series coefficient 的 formula 就可以通过一个 straightforward 的 computation 得到。OK， 那我觉得大家可能稍微需要就是特别注意的就是说就比如说在这个 time shifting 这边。其实我的 statement 里面并没有特别去强调x of t 或是 x of t 减 t naught 的这个 period，OK， 但是当你提到这个 Fourier series representation 的时候就是说你 implicitly assume 他们是会拥有同样的这个 period，OK，well at least 就是说这个x of t has a period of capital T, and then for this relationship to hold, you would also need to show that x of t minus t naught also has this same period. Okay. So we can do one more example. So in this example, we're looking at the time reversal, right? Time reversal. So if x of t has Fourier series coefficient ak, then you can show that x of minus t has Fourier series coefficient a sub minus k. Okay, so time reversal in the signal corresponds to a time reversal in the Fourier series coefficient as well. Okay, so again, this is straightforward to show. Okay. So first of all, if x of t is periodic with period capital T, then so would its time reversal. Okay, so I'm going to neglect that discussion there. And to get the Fourier series coefficient of x of minus t, okay, so you could okay to get this Fourier series coefficient for x of minus t, you could apply a formula similar to something above, but actually this could be observed quite easily by just writing out the Fourier series representation of x of minus t. Okay, so for x of minus t, right, the Fourier series representation is just summation of ak e to the j k omega naught minus t, right? So this is just the Fourier series representation of x of t with t substituted with minus t, which will give you x of minus t, right? Now, suppose you do a change of variable where you set m equal to minus k, then you again have a summation from minus infinity to infinity. But here you have a sub minus m, and up here, right, if you combine this minus sign with k, you get j m omega naught t. Okay, and this is the Fourier series representation for x of minus t. So this is saying that, so this shows that the Fourier series coefficient of x of t corresponding to the complex exponential e to the j k omega naught t is a sub minus k. Okay, so this is essentially what this notation expresses above. Okay. Now, consequently, okay, suppose that you have an even signal, right? So suppose that x of t is even. So if x of t is even, this implies that x of t is equal to x of minus t. Right. So if x of t is equal to x of minus t, then a sub minus k must be equal to ak. Okay, so then ak is equal to a sub minus k. Okay, which means that the Fourier series coefficient is even as well. Now, on the other hand, if x of t is odd, in other words, x of t is equal to minus x of minus t, okay, then this means that ak should be equal to minus a sub minus k, which means that the Fourier series coefficient is also odd.